All right, hello everyone. So welcome to Wednesday's lecture. This is atmospheric dispersion modeling. We're going to talk a little bit more about this. We started talking about this on Monday, but I'd like to go over a few more things and hopefully we can get through this section. And then on the following Monday, we will be doing some problems in class. So bring your calculators and maybe your books and you can work on that. All right, so we talked about what types of sources we have: point source, line source, volume source. Of course, when we're focusing on atmospheric dispersion modeling, we're focusing on a point source, and in particular one that is producing a non-reactive pollutant from an elevated source. And we're going to simplify things and use steady state concentrations. And we're going to use this Gaussian or normal distribution, which describes how the particles are distributed as they disperse from the plume itself. All right, so we talked a little bit about the axis orientation. So our 0, 0, 0 point is right at the base in the center of our stack. And we have X in the direction that the wind is flowing. We have Z in the upward direction. And then we have Y and negative Y to the left and right, respectively, if we're facing the downwind direction. So once we understand this, we can start digging in. So this is our kind of profile. This has a little bit different notation than what your book does, but essentially what it's saying, we have this actual stack height, which is actually how tall our stack is. And then we have what's considered to be plume rise. And it's a little difficult to see on this drawing right here, but this center line rises and there's some sort of delta H at which this rises from the top of this stack. And that would be our plume rise. And then if we add together our actual stack height and that plume rise, we get this effective stack height. And we'll talk a little bit more about that in a bit. Okay, so to get right to the heart of what we need to know, this is the steady state solution of a bunch of partial differential equations that's developed from mass balance and yields this Gaussian dispersion equation. So this is what this entire chapter is based on, and super important equation for you for solving any of these problems. All right, so let's go through a couple of these terms. So first, we're solving for the steady state concentration. This is at some point X, Y, Z at a concentration of, let's say, micrograms per cubic meter, which is typically the most common units to use for this type of a solution. And then we have our emissions rate. This is a mass emissions rate of our pollutant, and this is in micrograms per second. We have 2 pi, we have U, and we're going to talk about that. That's this average wind speed, but this average wind speed at stack height, which is a super important detail, and is probably one of the things that students miss the most in solving this type of problem. So we'll talk about this in a minute, how we get the average wind speed at stack height when we're usually measuring at a different height. And then we have this Y and Z horizontal and vertical spread parameters, or dispersion coefficients, if you will. And we'll talk about those in a minute, but these are able to be found either through your figures 20.7 and 20.8, or through equations 20.3 and 20.4. Now, 20.7 and 20.8, those figures are great to use if you're trying to solve something very quickly. So for example, the FE exam, I believe, uses something very similar to those figures to be able to help you just get through the problem quickly. But if you want to have a little bit more accuracy, because the way that one person reads that figure might be very different from the way another person reads the figure, we have these a little bit more accurate equations 20.3 and 20.4, which we can use to also calculate these. All right. So now we've got this term, and then let's look at these terms right here. The only other pieces of information that we need the y from our XYZ coordinate. We need the z from our XYZ coordinate. And we need this big capital H. This is our effective stack height. As I mentioned before, it's this actual or physical stack height plus the plume rise. And we'll talk about how you can calculate that in a minute as well. So looking at this equation here, there might be one thing that you think we're missing, and that would be our x value. So we have no x explicitly written into this equation. However, that doesn't mean that x does not play a role in this equation, and you'll see that a little bit more in a bit, but primarily where it affects is with these dispersion coefficients in the y and z direction. So once we have that, now that we've kind of talked about all of the little pieces here, let's sort of look at what this means and how we can understand this equation a little bit better. Okay, so the first part, well, I mean, the first part I should say is this piece right here. This is really looking at the source and sort of describing the release of the particles. And then afterwards, we're starting to look at how they spread in different directions. So in this case right here, so this first e to the power of this parentheses term, this is really referring to the dispersion in the y plus y and negative y directions. And so it's kind of obvious we have this y term here, and we also have this y dispersion term here. So what this is doing is just trying to describe how the pollutants move in the y direction, away from the center line of that plume. Okay, so pretty simple there. But oops, went a little bit too far there. So why do we have two terms here that both have the z in them? So one of the things that I like to kind of show is this right here. So we have this z minus h, h being our effective stack height, right? And so that's after we've added in the actual stack height plus the plume rise, we get to this level right here. This is our actual stack height. Now, this this blue line right here represents z minus h. And so you can tell that this is looking at how far upwards in the upwards direction we have this dispersion going. And then we have this red term right here where we're looking at z plus h. So if we look at what z plus h is, it takes us all the way down below the ground, sort of this mirror image. And so you might think, why would we have z plus h? Well, let's see if we can take a look at a little bit of drawing here. If I can get this to work for us. Okay, so I'm not finding the whiteboard for some reason. So we're gonna just draw right on here and do that like so. Okay, so excuse my poor drawing here, but this is our stack right here. And this is our Z direction. And so then I'm going to switch color really quick so we can draw kind of the, this is going to be the center line of our plume, right? And then we're going to have plume that kind of disperses from that in different directions, right? Now, if we continue this out, and this is the ground right here, eventually this plume hits the ground, right? And the plume cannot continue below ground. There's no going into the ground here. So if you are a particle and you're flying along and you're on the outside of this plume and you hit the ground, where do you go? Well, you actually get reflected back up off of the ground. And what that means is that once this plume hits the ground, you're going to get this area right here where there's more particles due to just the first the particles coming this direction away from the plume, but then also particles that are bouncing off of the ground and kind of doubling up on each other, if you will. And so because of that, we have to use this sort of mirror image model to take into account this area right here. And hopefully you can see where I'm pointing, this area right here, where we have sort of this doubling up due to the bouncing of the plume off of the ground. Now you can imagine that if we were to draw this really, really small, and so let me get back to my drawing here. So if we drew this, this is now our stack right here, very small. And this, let's say, is our plume center line. I'm trying to draw very small here so that we have lots of space. And this is our ground down here. And then we have our plume that's hitting the ground. And of course, you know, it's flying in this direction as well, but it's bouncing off the ground. And then you can imagine that as this continues, this whole area right here, we're getting more and more bouncing off of the ground. So we have to take into account this area right here, which will consist of the particles coming in this direction and this direction, but also particles bouncing off the ground. So hopefully that sort of makes sense to you, and that we have to sort of use this mirror image. And so because of that, let's see, we'll clear all of these. So because of that, we have two components here. We have this component, which is sort of the non-mirror image component, and then this, which is representing the mirror image component from the bouncing off of the ground. All right, so that's our equation here. Now, let me step back and talk a little bit about these horizontal and vertical spread parameters. So there's two ways to find this, as I mentioned. You can find them from figures 20.7 or 20.8. Now that also requires, you know, having good eyes and, you know, making straight lines and things like that. But it can be done, and you can get fairly accurate results from that. However, if you want to sort of ensure or double check your numbers, or maybe have a little bit more accuracy, you might want to use these equations right here, which are 20.3 and 20.4 in your book. And you'll notice this is where the x comes into play. So they are a function of x, but they're not a direct linear function of x. So what we have here are these curve fit constants A, B, C, D, and F. And these can be achieved or retrieved from table 20.2. And you'll also see that these are a function of x in a way, or C, D, and F at least, are a function of x is in as much as a certain set belongs to x values that are less than a kilometer, and a different set belongs to x values that are greater than 1 kilometer. A and B do not depend on x. Now, the other thing they depend upon is the stability class A through F. We're going to talk about that in a minute. That just indicates how stable your air is, so how much mixing will go on. And we'll talk about that in a minute. But to kind of get back to these really quickly, you may notice that there is no value or set of values C, D, and F for x equals 1 kilometer. And so if your x value is 1 kilometer, what I would recommend doing is calculating these terms for both the x is less than 1 kilometer and x is greater than 1 kilometer, and you'll see they're fairly close together. And so either way, you can pretty much make it work. If there's some difference there, you might be able to sort of take the average of the two values. So we're going to need to calculate the y dispersion and the x dispersion. And one big piece of information that you will need to calculate these is, first of all, their units. When you calculate them using these equations, the units of these will come out in meters. However, you must use x in kilometers. So that means that if x is 1 kilometer, you're going to put 1 in for x. And that's super important. That's another area where it's super easy to miss, because we're not used to putting in kilometer values and then getting out meter values. But this is just how they did the curve fit. And so we need to follow that convention, and also make sure that we're using table 20.2. You'll notice, we'll talk a little bit later, there is another set of kind of values or coefficients that use very similar A, B, C, and so on. So it's all in this chapter. So you need to know which table to use for the correct A, B, C, D, F values. Otherwise, you're not going to get the right answers. So make sure this is related to table 20.2 and not another table in your book. So this is the main points that I'd like to make around these dispersion coefficients. So once we know our stability class, what x value, we can find our A, B, C, D, F, and then we can plug in here with our x value in units of kilometers and get out dispersion coefficients in units of meters. Okay, so once we, now we kind of have all those pieces, we're going to talk a little bit later about stability classes and so on, but for the most part, if we knew all of that, we could go ahead and plug in to that big long equation and get what we were looking for at some sort of x, y, z coordinate. And one of the things that we often want to do is simplify things. So in many cases, we don't care as much about let's say, a location that is 20 meters off the ground. And so a lot of times, we care about ground level concentrations just because that's where we live. We live on the ground level. And so most of the time we care about Z equals 0. And then the other thing that we often care about is center line or Y equals 0 concentrations. And the reason for that is because we know that the highest concentration will always be along the center line of that plume. So that means that if we're concerned about, let's say, the maximum downwind ground level concentration, it's going to be along that x-axis. And so we can rewrite a new equation that's a little bit more simple than that big long equation that we showed a moment ago. We can rewrite this with Z equals 0 and Y equals 0. And that simplifies to this equation right here. And now you can see that we really don't have any Z or Y values here. We only have the dispersion coefficients, our wind velocity at stack height, and then our actual stack height, or excuse me, our effective stack height right here. So what I did, just to give you a sort of an idea of what this might look like if you were somewhere looking along this x-axis at ground level. If you were walking along this x-axis, let's say from the 0 point right at the base of the stack itself and walking in the direction of the wind, what would the concentrations be that you'd see? And so I just plugged in, for example, 100,000 micrograms per second mass emissions rate, a stack height wind velocity of 5 meters per second, and then an effective stack height of 20 meters. And I used a stability class of C, which we'll talk momentarily. And I plotted the concentration of in micrograms per cubic meter over that distance. So you can see that, the concentration goes up very sharply. We hit sort of this maximum, and then we start to decline the further away along the x-axis that we go. And so by the time, we're, let's say, somewhere around 0.25 kilometers away from the stack, we're going to start to experience the highest concentration here, which is right around 7 micrograms per cubic meter. So one of the ways that you can find the maximum downwind ground level concentration is going to be to use this equation and, let's say, plot out what this graph looks like. Now, you may need to add a few more points just to make sure that you're not missing any that kind of go up a little bit higher. But you could plot this out potentially at using multiple different x values, and then find where is the maximum, and that would be your maximum. So that's one way to do it, although a little bit tedious because you're going to have to develop a graph for each single condition, and you're going to have to put in enough data points or x points to be able to really see where that maximum occurs and what that maximum concentration is. So there is a way to do this a little bit more simply. I should have put that right after this, but we're going to talk about stability classes first, and then we're going to come back and I'm going to show you a different way that we can find this maximum downwind ground level concentration. This right here allows us to calculate any of these concentrations along the x-axis, but we often want to find where is the maximum and what is the maximum. And so we can do that, which we'll talk about in just a minute. Okay, so stability classes, this is really describing how stable or unstable the air is. And with stable air, we have less vertical motion. So it just sort of sits there. There's not a whole lot of, up and down or, spreading or mixing, let's say. That means that it's really bad for air pollutant dispersion. And so the plume is going to sort of hold together a lot longer as it goes away from the stack. Now, unstable air means more vertical motion. So that's good air pollutant dispersion. So lots of mixing. And so we'll have a lot more dispersion. It may mean the plume will hit the ground more closer to the stack itself. But it also means that we'll probably have lower concentrations because we'll have better mixing and more dispersion of that air pollutant. So A is going to be very unstable, meaning lots of mixing, and F is very stable with very poor mixing, and D is sort of in the middle, being neutral, and we have all of the classes in between. And so the primary factors that we use to determine this are going to be wind speed and incoming solar radiation. And we do have a table in our book. And so I don't believe I have this on these slides, but we have a table 20.1 in our book. That's on page 662. And depending on the surface wind speed and the incoming solar radiation during the day or cloudiness during the night, we can determine what stability class we're at. Now, a couple of points about this. This table uses the surface wind speed. So this is the only time you're going to be using surface wind speed. So you're going to be using surface wind speed to determine the stability class. Now, surface wind speed, if you read all of the little tiny fine print below the table, which you should, if you read that, you'll notice that surface wind speed is measured at 10 meters above the ground. So when we're saying surface, it's not really at z equals 0, it's at z equals 10 meters. So it's also really important that you read the other little notations below that table so that you can really understand how to use that table and find the correct stability class for whatever condition that you're given in a problem. So then once we've selected the stability class, again, this has a direct impact on our dispersion coefficients, as you saw previously in table 20.2, based on our stability class and where whether our X is less than a kilometer or greater than 1 kilometer. We have different values for the A, B, C, D, and F, which go into the equations for our dispersion coefficients. Okay, so wind speed. So as I just mentioned, surface wind speed, 10 meters off the ground. The only time you're going to use this, and I'm going to say, put it right here, only used for table 20.1. And then any other time you see wind speed, it's going to be wind speed at stack height. So I'm going to put that right here, that all other U values are wind speed, or is wind, or are wind speeds, let's say, at actual stack height. So that means h, little h. So that means that a lot of times we start off being given a surface wind speed from some, let's say, weather station that's measured it. And when they say this is the surface wind speed, we know this is 10 meters off the ground. We'll go to our table 20.1 and use it there to come up with our stability class. But then after that, to use wind speed in any of our equations, we need to adjust that wind speed for the actual stack height of our stack. So that kind of brings us to this point right here, that wind speed increases with increasing elevation. So that means if you were, let's say, at sea level, the wind speed you're experiencing there is going to be probably less than if you climbed a big, huge ladder up to the top of a tower. You're going to have more wind up at the top of that tower than you would near the ground. And that's due to this principle right here. There's a number of reasons for that, including the fact that things on the ground tend to sort of disrupt, wind flow and so on. But essentially, we need to adjust our surface wind speed, which we usually plug in for U1, and calculate U2, which will be the wind speed at the top of our stack, or at stack height, actual stack height. And so then the pieces of information that we need are going to be Z1, which if we're starting with surface wind speed, this is going to be 10 meters. And then we need Z2, which is going to be the actual stack height of our stack. And then the last piece of information we need is this P. This is an exponent that's related to stability class and surface roughness. And so you will use table 20.3. So 20.3 lists different stability classes and requires you to select either rough surface or smooth surface. Now, rough surface correlates to an urban environment, and you can imagine why. That means that we have buildings, we have structures, maybe other things that disrupt the wind flow. And so if you think of it sort of like the inside of a pipe, it's a lot rougher because we have a lot of built environment that's disrupting that flow through that pipe, right? Whereas in a rural environment, it tends to be more open. There's not a lot of structures. There might be a lot of kind of agricultural fields, which are nice and smooth relative to the urban environment. And so the smooth surface would be a rural environment. So we have to identify whether it's urban or rural, and then use the stability class to select this P value. That's again from table 20.3. Now we can adjust our wind speed. All right, so I'm going to clear all of this. We're going to move to the, this keeps going a little fast. So quick note on averaging time. This is not incredibly important, but it can be if you're looking at different, let's say, concentrations developed from this Gaussian equation, and you're trying to compare it to, let's say, the National Ambient Air Quality Standards, where they have different averaging times for the concentrations that they're looking at. So here, the Gaussian equation uses this 10-minute average concentration. So if you are trying to adjust that concentration that's at, that you get from the Gaussian equation, which correlates with a 10-minute average concentration, and you want to compare with, let's say, a standard that's either that has either shorter averaging time or a longer averaging time, you would pick up one of these two equations to use and adjust accordingly. And this is really just pretty simple, nothing else needed other than averaging time in minutes of your standard or whatever you're trying to convert it to. So for example, you would use this, let's say you have an averaging time for one of your pollutants that you're looking at, and see if we can just look really quickly here. So if we have our national ambient air quality standards, maybe we have, let's say we're looking at a pollutant that's non-reactive. Maybe it's a 60-minute averaging time. Our Gaussian concentration that we get is going to be this 10 minutes averaging time. And we want to compare to see, will it meet the 60-minute averaging time concentration given for, the national ambient air quality standards. We would plug in 60 here for T, we'd plug in what we get from our Gaussian equation, and then we can calculate what this 60-minute averaging time concentration would be and compare that then to our standard from the national ambient air quality standards, something like that. Okay, so I promised you before that I would give you an easier way to find your maximum downwind concentration and distance, and a little bit easier than, say, plotting it out and trying to find it graphically. So we can do this. Of course, this is located along the center line, so it's along the x-axis. Y and z are both 0. And it's dependent on the stability class, effective stack height, wind speed, by the way, at our actual stack height, and our emissions rate. So if we have this, we can come up with this equation that our C max is equal to Q, this is our mass emissions rate, U, this is our wind speed at actual stack height, and then this term right here. And a lot of times this can be confusing because this is one term. This is all one number. Don't try to split it up or, try to, split the C max and U max and Q max. Just treat this as one variable. This variable you can get in 2 different ways. So you can either get it from figure 20.9. So I'll write that right here. You can use figure 20.9 to get, let's draw right here, this right here. You can get either from figure 20.9, where you have a different, and we'll talk about how to use that in class on Monday. But you have different stack heights, effective stack heights, and you have different stability classes. And if you find the effective stack height and the stability class on the stability class line that you need, you can draw a line downwards and find this CU over Q max using this figure. It can be a little bit tricky, and there's not always an easy way to read this. Sometimes your effective stack height goes above what's on that figure and so on. So another way, a second way to do that is to use this equation right here. So you can calculate it specifically using this equation right here. Now notice that we have this A, B, and C, and D here. This is not the same as the ones that we use for our dispersion coefficients. These are completely different. Don't ask me why they decided to use the exact same variables or notation for this. But these all can be obtained from table 20.4 based on the stability class. So don't be fooled by the 2 different sets of these variables. One will have an F and one will not. So that can help to kind of differentiate. But just make sure that when you're using this equation right here, that you are using the correct A, B, C, and D, and that you're getting it from 20.4. So very, very important there. All right, so this is going to be probably the, one of the main things that you're going to be using for calculating the downwind maximum concentration, especially for your group project. So once you have Q and U and you have this term right here, you can plug in and find what that concentration is going to be. Now, to find the distance, and I guess I don't have much here, but to find the distance, you're actually going to have to do one of two things. To find the distance, you'll have to use figure 20.9. I know I said that can get you this term right here, the CU over Q max term, but it can also help you find the X max term. And X max is where, so this will help you get X max, which is the X value where that maximum downwind concentration occurs. So, so that's, one way to do it. Now, there are other ways to do it as well. We're not going to get into that, but if you run into issues with your project and you need to use a different method to find X max, or if you're having trouble, just come see me. I've got other ways for you to solve that. So, all right. So next up, we're going to talk a little bit about temperature inversions. This is an important concept, especially for sort of, modeling what happens with these pollutants that come out of the stack. You'll also remember that these temperature inversions are, the cause of a lot of those tragedies that we talked about the first day of class. And we need to kind of understand, first of all, the normal conditions is that we have warmer air near the ground, and that as you go up, it's colder air. We kind of all, expect that, that's why we can see snow on the mountain and yet have a nice 70 degrees here in San Diego. So the higher elevation, the colder it gets. And so this is kind of normal conditions. Now, what happens with the temperature inversion is where this sort of warm layer of air slides into the middle of a sort of cold air. So we have cold air above and then kind of cooler or cold air relatively below this warmer air. And because of that, we know that as this kind of air goes up here, the warmer the air, it might be rising, right? So it would rise away from the city, but then it kind of hits this warm air and it just sort of goes sideways. And so because of this warm layer here, it sort of acts as a lid on all of the pollutants down here that might otherwise have continued going up. So you can see here, this might just continue going up, dispersing away. And that's what we expect with our normal Gaussian dispersion equation. We just sort of anticipate that if there's a plume, that it would just continue to rise and rise and rise, and that the edges of it would continue to expand upwards. But that's not the case if we have this inversion layer. Then we have pollutants that rise and rise and rise, but there's a point at which the inversion layer sort of prevents that from continuing to rise and sort of traps it down here. And so we need ways to model that condition as well. So it acts very similarly to a surface, sort of like what we talked about when we looked at the ground, where it reflects the pollutant off of the ground when the plume hits the ground, right? In a similar way, now we have a lid at the top that's reflecting pollutants downward. So as they come up, they hit and go downward. So what I'm going to try to draw here for you is that, let's say we have our little stack right here, and I'm going to just draw the plume center line here. And so eventually it kind of stabilizes, right? And then this is going to be the ground right here. And then let's say this is our temperature inversion layer right above it. This is our inversion layer. Right? And it acts sort of like a lid, as I mentioned. So now I'm going to change the color here. If we have the edges of the plume, now no longer are they just continuing to go up and up and up as they normally would. They would normally just continue on their way up like that. But now instead, we see it reflecting back down. And we have this area right here that's acting kind of as this reflection zone, right? So it's where it's reflected back. Now let's look at what happens at the bottom of the plume. The bottom of the plume continues down. This is what our original Gaussian equation takes into account, is that eventually it kind of hits the ground, and it kind of reflects back up. So we kind of have this, reflection area, if you will. And of course, this continues. But let's continue this on. So this is our reflection zone, right? Eventually, it might hit this and reflect back down. And in a similar way, we might have this one coming down now, hitting the ground, reflecting back. And essentially, we end up in a condition where we have infinite reflections. It's like being in a room where you have two mirrors opposite each other, and you can look in one mirror and see infinite reflections of yourself. And that's essentially what's happening, that it bounces back and forth, back and forth, back and forth. Now, it doesn't mean that the concentrations remain the same, because they are still dispersing in the y direction. So we are still, decreasing the concentration over time. But we need to account for this. And so if we are modeling a trapped plume, now we have this term right here, which is saying that we need to sum up what's in these brackets from negative infinity to positive infinity. But that's not really possible in the real world, right? I mean, without doing some really funky math, we're not going to get there. So what people have found is that adding up just a few of those terms is enough. So it's sort of like saying, we're going to add the terms for, let's say, this area and this area and this, reflection, and this reflection and this reflection. But after about 2 reflections, now we're dispersed enough in the y directions that it's not making a huge difference, that, the small concentration we have is not really being reflected back and forth as much. And so we can get a fairly accurate representation by just using a j from -2 to +2. And so where you see that is going to be right here. And we're going to also have this other term involved other than the j values. So we'd have to plug in j values from -2, calculate this whole thing, and then add this whole thing with a j value of -1, and then 0, then 1, and then +2. So we have those few numbers that we add up of this term all together as 1, and then we multiply by all of this right here. So so we have this j term, and then the other term that we need to know is this L term. This is going to be the height from ground to our confining layer, and so or inversion layer rather. So this right here is going to be L. And so plugging all of that in, we can get this term right here. And so this term, just keep in mind, you're you're adding up multiple things. So Excel can be really useful for this. And then you're going to multiply by this right here, these terms right here, and then you'll have your concentration downwind at some Z and Y and X coordinate. All right, so that is a temperature inversion. So it is a little bit more work, but with Excel, we can make it very, very much easier. All right, so let me get back to my spotlight. Another thing I wanted to just point out is fumigation. Fumigation, we have a different equation for this. Now there's different types of patterns for, you know, how plumes will emerge and how they will work based on temperature, how the temperature over the height, you know, as you go up in height will look. And so here we have fumigation. This is where we typically have this sort of low temperature in the middle, high temperature here, and then higher temperature above. So kind of the opposite, if you will, of a temperature inversion. And we have an equation for it here. We're not going to really deal with these other types of movement. But I did want you to just see that we have other types that we can have, you know, find different equations and models for based on how our temperature and height profile look. All right, so this is one way to treat the stable layer that's aloft without having to do let's say, as much of the addition that you saw before. So this is an equation that they came up with. This is only for if you have an X value that's greater than 2XL. What does that mean? Okay, so here is your X equals 0 right at your stack, right? Then this is our center line of our plumes. This is our effective stack height. This right here, where the top layer hits, the top of the plume hits the stable layer aloft, that X value associated with it. So this is not a height. This is along the X axis here. So the X value right here to here, that will be XL. So XL is basically saying the distance from your stack along the x-axis, where up above the plume is first starting to reflect off of the stable layer. So here it would be this distance right here would be XL. Where you have XL, if you are looking for a concentration that is way further down, meaning greater than 2XL. So that means that, let me just get back to my drawing here. So this right here, just to be clear, this distance right here is XL. So even though I kind of have the arrows going that way, it's a little bit misleading. So I just want to clarify, this is XL in this direction right here. So if we do another kind of XL value, let's say, in this direction, not exact, but you'll get the idea. That means that the only time that this is, that we can use this equation is if we're looking for a value in some sort of region here, you know, oops, I guess I should, let's just erase this real quick. and I'll put this in text. Put it in green. Well, put it in black. Can use equation here. So anywhere beyond 2xl, so if your x is greater than 2xl, so fairly far from, where it hits that that stable layer loft, then you can use this equation right here. It's a little bit simplified. And then we have here a different equation for our Z dispersion coefficient. And so here now our Z dispersion coefficient at XL, so right at this X equals XL, our dispersion coefficient is going to be this equation right here. So this is the L, which is our stable layer height, minus our effective stack height, which is right to where our center line of our plume is. All right, moving along. So I tried to kind of bring some of these equations together into a table for you to sort of summarize, because I know this is a lot of dense information and you're probably overloaded at this point. But hopefully this can help clarify what different ways you can use to find, your concentration. So here we go. This is if your X is less than XL. So so these are all for, keep in mind, with let me just clarify here with some text that this is all for temperature inversions. So based on different X values that you might have, you can use either this equation up here or this equation, or you can use both and interpolate. So that's pretty much how you're going to calculate with a temperature inversion. Come to this table and find which is the appropriate equation to use. All right. Okay, quick thing. Usually I'll ask you in class, what's the difference between tall and short stacks? But it is kind of obvious. Tall stacks, we have certain conditions. They're generally 2.5 times as tall as the tallest of the nearest buildings. They have high buoyancy and exit velocity, significant plume rise, and so on. Short stacks are generally smaller. Now, when they're smaller like this, so less than 50 meters, for example, it can be more tricky to model the plume rise and all of the other associated things, because there's going to be buildings and terrain around it that can disrupt how you model that, that plume. So for the most part, we're going to be sticking with tall stacks and assuming that for our group project, all of our stacks are tall stacks. The reasons that we build tall stacks. So this is in Kazakhstan. This is a comparison of Kazakhstan's thermal power plant stack versus the Eiffel Tower here. Our main purpose is to reduce the local concentration. So the higher we build it, the more dispersion there can be before the plume hits the ground. And hopefully that means that we have a lower concentration when the plume does reach the ground. And so people are not as exposed to that plume. Now, keep in mind that mass emission rate is not reduced by having a tall stack. What that means is we're still spewing the same amount of mass out here. It's just that we're mixing it a lot faster before it can hit the ground. So we're mixing a lot more, I should say, before it hits the ground. And so even though we're putting the same amount of pollutant out into the atmosphere or into the environment, we are hopefully mixing it with cleaner air before it gets to the populated areas of the ground. So we have to sometimes think about the cost of building a stack taller versus, let's say, shorter. And so this is often one kind of question that engineers will wrangle with when they're developing new processes or power plants or things like that. So if they're designing a tall stack, they would want to first analyze the meteorology. So you're going to be doing this for your project. So you would look at, historical meteorology data and so on, make a preliminary hazard assessment. So what's nearby? Where does the wind blow typically? What are the stability classes throughout the year and so on? Then test various cases of physical stack parameters, height and diameter. You can change those, and those change different parameters and how that plume will behave. And so you're not going to be doing that for your project, but I wanted you to know that it is, primarily the job of the engineer to sit there and test out different heights, different diameters, so on, looking at what we call worst case meteorology to be able to understand how the stack that they're designing might influence, health and the health of humans and the environment around it. They'll have to consider effects of local terrain. Is it urban? Is it rural? And things like that. And then reviewing their results and do they make sense? So this is so important because as engineers, we have to always look at our final answer and say, does it make sense? Because if it doesn't, then we need to go back and double check. This is something that a computer at this point can't do for us. So this is really a big heart of where our job lies, is to really understand the full design procedure, all of the modeling and everything, so that we can judge whether it makes sense or not, and know where to go if it doesn't make sense. All right, so finally we're to plume rise. So here we're going to talk about how we calculate plume rise. So until now we were just kind of assuming there's some plume rise that we know. And so here, this is our actual stack height. Your book calls it little h. And then we have delta little h, which is our plume rise. And then we add those together to get our effective stack height, big H. And so this is, these are the three that you really need to know which is which and how they all go together. So we're going to talk about now, obviously we can take and measure this, this actual stack height. But in order to get this, our effective stack height, we need to know what our plume rise is. And so I'm going to show you here how to figure out what your plume rise is. Okay, so let's start with a little bit of physics. We all know if we do a free body diagram on something that, we can sum up forces. And the reason that we have the plume even rising to begin with is that we have more momentum and buoyancy forces in the upward direction. So we add these together and our upward force is much greater than our drag force, which is in the opposite direction or downward direction from our plume. So what happens is we have the plume, these forces, the momentum comes from the flow of this gas through the stack and upwards. So the momentum is really due to the fact that we have some flow rate going upwards. And then our buoyancy is due to a difference in density between our plume and the atmosphere around it. And as we have our plume rise, eventually our buoyancy terms change because we have changes in temperature and so on. Eventually our buoyancy forces change and so on, that now it gets to a point where the sum of our momentum and buoyancy equal the drag force. And in that case, now we have sum of forces equals 0. And that's why our plume center line eventually levels out horizontally. So until it levels out horizontally, we have more upward forces, but then eventually they become equal to the drag force, and we get, that leveling of that plume rise. So we have 3 different methods in your book about how to calculate plume rise, different formulas and so on. The Holland formula, the Concaw formula, and the Briggs method. Now, most kind of common EPA models use the Briggs method. It's a little bit more complex. It requires more information, and it was developed a little bit later. But Holland and Concaw can sometimes also be useful. And so they're a little bit easier to calculate. So we're going to learn all 3. And for your project, you're going to be doing all 3 of these methods to determine which one will give you worst case conditions. So Holland formula, the things that you need are going to be the stack gas velocity. And in this case, so let me just draw quickly here. So we have the top of our stack here. There's some velocity that gas has as it's coming out that's due to the flow rate of that gas. This is Vs, and this is our stack gas velocity in the upward direction. This is what contributes to the momentum force. Then we have stack diameter. So that's going to be right at the top here. Our stack diameter right here. This distance, that's our ds. So that's our stack diameter. And then we have a heat emissions rate. So this is a little bit different than the mass emissions rate. It has to do with how much energy is carried in the gas itself, which is carried as temperature or higher temperature. And so we'll have this heat emissions rate QH. And then we have the mean wind speed at stack height. So of course, that is our U that we've talked about before at our actual stack height, right? And so if we have those, then we can use equation 2013 in our book to come up with the Holland formula, and it will calculate our delta H for us. Now, Concaw, a little bit more simplified. We have a heat emissions rate and the mean wind speed at stack height. So if we don't have all of this other information like stack gas velocity or diameter, we can instead use the Concaw formula and equation 2014. But if we want to have a little bit more information, we're going to use the Briggs method. So first of all, there's a few steps to this. This is not a one-step equation, one and done. You have to go through these different steps. So the first step is calculating what's called the buoyancy flux. And this can be calculated using equation 2019. And we'll typically use a molecular weight for our stack gas of about 28.9 or similar to air. Then once we have our buoyancy flux, we're going to calculate the downwind distance to the point of the final plume rise, or XF. And what that means is if we are, get back to our drawing here. If we have a little, this is our stack, right? And we have some sort of, this is our center line of our plume rise, right? And we want to find where does it finally get to that, final plume rise where the center line no longer is rising anymore. If this is our X direction right here, this is going to be our XF. So that's going to be our XF. And then we can calculate that, that downwind point. We want to figure out where that's going to be along the x-axis using either equation 2015 or 2016, depending on the FB value. And if you take a look at that equation, if we have an FB value that's greater than or equal to 55 meters to the fourth divided by seconds to the third, then we can use 2015. And if we have one that's less than that 55, we would use 2016. So just check out the equations in your book. It'll have those restrictions there. Once we have our XF, then we're going to calculate our plume rise delta H. And it matters where our X is, because if our X is somewhere, let's say within this XF value, you can see that the plume rise right here at this point is not going to be as much as it is out here. And so we have a different equation that relates the plume rise for this section right here versus this section right here, where that plume rise no longer changes with increasing X values. So if your X value that you're looking for that concentration at is somewhere less than XF, then you're going to be using 2018, equation 2018 for this section right here. But if your X value is greater than or equal to XF, so somewhere in this region, then, or this region rather, you're going to use 2017. So it's just looking at different parts of the plume rise. All right. So those are the main plume rise formulas that you're going to be using. And I just want to mention a couple more things that, of course, this doesn't capture the entire picture of everything. Even our air mod, which is the model used by EPA outside of California. So California has their own, but outside of California, this is a typical model used by EPA. They are showing that there can be issues with especially buildings and other things like that, where you can get these cavity regions. So there's a lot of work being done around computational fluid dynamics to sort of simulate this and improve some of those models beyond just the regular Gaussian model. So if you're interested in modeling or air pollution, this is a great area to get involved with. So building downwash is really where you have, let's say, the stack right here, and you have a building downstream, and it's going to be influencing what happens with the plume. So here you have even air that has to go over the building, and that can push your plume. So for example, if you have a shorter stack and here's your building, you might start to get eddies behind it. If the stack is shorter than the building, then it has to go up and over. So you have a different sort of plume. And then, this is where the stack is right on the building, tall, medium, short, and then further downstream. Now, even if the building is upstream, it can still affect your plume. So you can see right here, because the air has to go over it, it starts to kind of have its own shape, and it can influence how this plume interacts. So it can kind of push maybe the top down. This is, very non-influenced by the building. And then these are where we start to see a little bit of influence. So just some interesting additives to think about how, buildings and other structures and things like that, even if they're not that close to, or even if they're upstream of your stack, they can still influence the plume and what it looks like. All right, here's all of our kind of different EPA approved software models. You can check these out if you're interested. Most of these, especially AirMod, you can get and use for various different things. Won't be really useful for this project, but if you're working in this area in the future, you might want some access to some of these models. All right, I'm going to stop there. Thanks for holding on and listening to my video here. Read your chapter 20 very, very carefully, look through the examples, and we'll be doing some examples in class, and I'll see you all on Monday. Bye, everybody.